Okay, so if we can't solve a problem by writing down equations, how can we solve it? I mean, that's how we've solved every problem all the way through physics so far. So what is this numerical solution that gets us the answer, but doesn't actually give us an equation for the answer? I mean, what could this be? This is not like physics as we know it. Well, let's take an example. Let's imagine we've got a three-body problem. So we've got object number 1 over here, object number 2 over there, and object number 3 over here. And they've all got some starting velocity and mass and position. And we want to work out where they're going to go. Now the trouble is, if you try to calculate, for example, where this particle is going to go, as it moves, the gravity is going to change. So at the beginning it's going to have a gravitational pull from this object and another one from that object, but as it moves over here, the gravity from this object will become stronger and that one will be about the same, but also these objects are going to move at the same time, and so the gravitational pull that was in this direction, if that object moves over here, might now be stronger in this direction, and so on. So you're trying to move an object where the direction of the forces on it and the size of the forces on it is constantly changing. So how can you possibly do this? Well, here's how. Divide the motion up into really small time steps. So we're not going to ask where is this thing going to be 10 minutes from now. We're going to ask where's it going to be 1/100th of a second from now. So it might only have moved from here to maybe just over there or even less distance. Now for this very short time step, but it's only moving a little tiny way, for that short time step there won't have been much time for this object to move or for this object to move. And going from there to there is not going to make much difference in any of the forces, because sure, you're a bit close to this object, so the gravity will be a bit bigger, but if it's a really small time step, that change is going to be tiny. It might be a 0.1% or something like that. So while we can't write an equation for the whole motion, for a very, very small bit of motion, we can just approximate that all the forces are going to remain constant. The gravity from all the other objects is not going to change for the short time scale to pretty high precision, like 0.01% or something like this. And that's what we then do. We work out where it's going to be one time step, 1 delta t, in the future, where delta t is small, whatever that means. It's got to be small enough that the forces don't change very much on that time scale. So you're now at a new position. You do the same thing for the other objects. You work out where they're going to be one small delta t, small time step forward. And now you work out the new forces. So there'll be new gravitational forces from the new positions of all the objects. And then using the new forces, you go and calculate another delta t forwards. So step by tiny step, you work out the motion. And each step is a very tiny one, but for each step we're assuming that all the forces remain the same. The force for this time step will be quite different from the forces from this time step, because by then all these objects will have moved to new places. But that's fine. All that matters is during the time step, nothing much changes. And if we have our delta t small enough, that should be very high precision accurate. So that's what we do. We break the motion up into a whole series of really tiny steps, small enough that we can make the approximation that nothing much is changing during each time step, and then we just add up lots of those time steps. And that's where a computer comes in, because each time step might be fairly easy to calculate. We just have to work out the forces. Say you're calculating this time step, you work out the forces at the beginning from where all the other particles are at the beginning, and then just assume they're constant and work out where it's going to be at the end of the time step. That's a fairly easy calculation, but there's a lot of them. You might need like 1,000,000 time steps to work out where something's going on. Now, back when this method was first worked out in the middle of the 19th century, people realized this was the way to solve the three-body problem. This is actually the method that was used to calculate the orbit of Neptune originally. And what they would do is they would use computers. But back then a computer was a person, or in fact a whole room full of people. What would happen is one person would do the calculation for this time step here to here, and then hand the piece of paper to the next person who'd work out this time step, and then on to the next person who'd work out this time step. And so, all worked out by hand, passing pieces of paper around a room with a large number of people in it, you could actually work this out. but it would sometimes take them years to do just one calculation. By the 1950s, 1940s, people had calculating machines. They'd put punch cards and turn mechanical machines to do it. And then from the 50s and 60s onwards, we had computers to do it. And computers like nothing better than to do simple calculations over and over and over again really fast. So it's the invention of electronic computers that's turned this numerical method, instead of being this very painful thing you did in absolutely disastrous circumstances and it might take years, to be something that you do all the time now, because it's actually quite easy. And it allows you to put a lot of complexity in. So this is how that three-body simulation I showed you earlier was calculated. All I've done here is exactly what we've just said. I've broken the motions up into lots of very tiny time steps and added them all up. And as long as you make the time steps small enough, you get very accurate predictions of the motion. It took about 1 million time steps to calculate this, but that's fine. That still only took a few seconds on a modern computer. And it can be used for much more complicated things. Here we've just got 3 objects moving around. Here is a simulation of the early universe where they're simulating about 10 million particles. In this case, they're simulating dark matter particles and gas particles coalescing after the Big Bang to form the very first galaxies. And so this wasn't done on my laptop in only a few seconds. This was done on a network of supercomputers and took probably weeks and weeks of work. But once again, this is a level of complexity you're never going to be able to handle just by writing down equations. Here's another astronomical simulation. Now we're simulating the motions of gas as a giant molecular cloud coalesces to form stars. So what we're doing is we're breaking the gas up into cubes, and each cube of gas we work out the pressure from all the neighbours and work out how it's going to accelerate. Now, of course, the pressure from all the neighbouring gas cells is going to change all the time as the gas moves around, but again, over a very short period of time, you can assume it doesn't change very much, and therefore calculate this whole thing, which is the formation of solar systems. What we've got here is a computational fluid dynamics simulation showing what's happening to the fluids around the landing gear of a plane. This was done by NASA. And once again, you're dividing the air up into tiny cubes and using a very fast supercomputer to simulate the pressure and density and temperature of the gas in all the cubes. And you can actually model what's going on about the fluid dynamics of a plane. Or here we have finite element analysis of a building exposed to an earthquake. So what we're doing is we're dividing the building up into lots and lots of tiny cubes, and for each cube we're working out the stress and strain from every neighbouring cube, and over the millions of cubes we can actually get an accurate calculation of how whatever design you have is going to work. So this whole numerical analysis stuff is very, very big business. Many people spend their entire careers doing it. Here's a twisting motion, and we're just going to take the very first simple steps into modelling situations numerically. But if you're interested in this, this is a huge thing that you can spend your entire career doing.